Newton's work. So at the surface, it will just simply be minus g times the mass of this object. So this you can think of as having mass m, radius r. And so he said the potential is minus gm over r. Then he said, if you project the particle up from the surface, it has velocity v, then its kinetic energy is going to be a half mv squared, where v is the velocity of light. He knew that the velocity of light was finite from Roemer's discovery of the finite speed of light by looking at the moons of Jupiter. So he knew that v was finite for light. In fact, he himself measured the velocity of light and got about 2/3 of the right answer. So that was pretty reasonable. He also knew that light carried momentum from experiments he had done in 1761 himself. So he thought that this was a perfectly reasonable approximation for what the energy of light should be. Of course, he had no idea what little m was. That's not so bad, as you will see. So if you calculate the velocity at infinity, we all know how to do that, you will end up with v squared minus 2gm divided by r. And obviously, v infinity is going to go to 0 if the following condition is true. So there will be v infinity goes to 0 at 2gm over v squared r is equal to 1. So this would be the speed of light. Amazingly, that's the same answer that you get in general relativity if you do the calculation properly. So he argued that this implied that if r was small enough for fixed m, there would be objects so condensed that light could not escape. And then he did some reasonable estimates about how big such objects could be. It is amazing that he got the right answer. There was a subsequent imitator, 1798, Laplace, who seems to be credited in the textbooks as having discovered this, but he didn't. Unsurprisingly, John Michell was a Cambridge man. He was at Queen's College until sometime in the 1760s, when he, unfortunately, I suppose for science, got married and took up a living in Yorkshire, where he was their local clergyman. Didn't seem to stop him doing this. So really the entirety of this course is about doing a general relativistic version of this and exploring its consequences. Now, before I do that, like everyone who does general relativity, there are issues of conventions to look at and units. So I will be very explicit about my conventions. My conventions agree with Hawking and Ellis and Misner, Thorne and Wheeler. And probably others. In fact, certainly others. They agree with Sean Carroll too. So if you have used any of those books, I should agree with them. And so for me, the metric signature is mostly plus, so it's minus plus plus plus. I will always assume a symmetric metric convention. Unless very exceptionally I do something otherwise. The consequence of that is that the definition of the curvature tensor is as follows. Del A, del B, acting on an arbitrary vector field VC, minus del B, del A, acting on VC, is equal to the Riemann tensor, with the indices going in the same order as here, contracted with VD. So that is my definition of curvature. And of course, this Riemann tensor will obey all the usual symmetries of the that you would expect. My Ricci tensor is going to be RAB, and it will be the curvature tensor contracted on the first and third indices. And the Ricci scalar is going to be R, which is RAB, GAB. So that defines curvature and metric conventions for you. Lastly, I have to deal with units. As we all know, it is a major nuisance to have factors of h bar, g, and c scattered everywhere, so I will abolish all of them. So I will use what are usually called natural units. Or possibly Planck units. They are the same thing. Simply depends on where you grew up, which one you think is the right one to use. And the way in which you do this is to simply contemplate the dimensional nature of the fundamental objects in physics, h bar, c, and Newton's constant, g. So if you think about the dimensions of these things, this has got dimensions of mass, length squared over time. And in CGS units, this is roughly 1.054 times 10 to the minus 27 ergs times seconds. Similarly, C, we know, has got dimensions of length over time. And in CGS units, that's roughly 2.997 times 10 to the 10 centimeters per second. Lastly, there's Newton's constant, which is one that's always hard to remember. This has got dimensions of length cubed over mass and time squared. So in CGS units, this is going to be 6.673 times 10 to the 8 centimeters cubed, grams to the minus 1, seconds to the minus 2. Now, if you stare at this, these things basically fundamental units of mass, length, and time determine what h, c, and g are. So having these things equal to some horrible numbers like this is a major nuisance. It's much better to choose your fundamental units of mass, length, and time to be such that h bar, c, and g is equal to 1. And that eliminates lots of horrible numerical factors, factors of g and c and h bar. So that's what I'll do from now on. Now that, of course, means that these set of relations here are going to be sort of turned backwards. You could, of course, if you like, invent a unit of time, let's call it the Planck time, by taking appropriate combinations of h bar, c, and g. In other words, eliminating m and l from these things. So an obvious thing to construct is h bar g over c to the fifth to the power 1/2. That's an object which has dimensions of time. It's called the Planck time, and if you need to turn this into seconds, it's 5.391 times 10 to the minus 44 seconds. So if you think about this a little bit, if you choose h bar g and c to be equal to 1, then the effect of that is going to be to say, well, 1 unit of time corresponds to this interval if you want to turn it into seconds. So if I talk about an interval of time which is 1, what I mean in CGS units is this rather brief instant, just over 10 to the minus 44 seconds. And you can do the same thing for lengths and masses. The Planck length is going to be equal to, well, it's obviously related to time and c, so it's h bar g over c cubed to the 1/2, and the Planck length turns out to be 1.616, give or take, times 10 to the minus 33 centimeters. So if I say that I'm talking about 1 million Planck lengths, I mean around 10 to the minus 27 centimeters. Lastly, there's a Planck mass. You can find something with dimensions of mass built out of h bar c and g. H bar c over g to the 1/2. And this is roughly 2.177 times 10 to the minus 5 grams. So when one measures things in natural units, these are the physical dimensions that you should be thinking of. So I am going to use these units where h bar c and g are all equal to 1. A consequence of that is that the Einstein equation simplifies. So that for me, the Einstein equation is going to be RAB minus 1/2 of the Ricci scalar times GAB, and then plus possibly, but not necessarily, a cosmological constant term, lambda times GAB. So this is going to be the cosmological constant. And that's going to be equal to 8 pi times the energy momentum tensor, TAB. So there's no factor of big G over c squared stuck in here, which will make life a little bit easier for us later on. I ought to say something about the sign of the cosmological constant. I do not know how many people went to Dr. Stewart's lectures. How many, roughly? Lots. Now, I believe that he did conformal diagrams of de Sitter space and anti-de Sitter space and Minkowski space. Is that right? Okay. So for me, but I don't know about him, you'll have to tell me. The cosmological constant is positive for de Sitter space. And negative for anti-de Sitter space. Was it that way round for him? Maybe. Well, it's that way round for me. And again, this will agree with what you will find in Hawking and Ellis, Misner, Thorne and Wheeler, and Sean Carroll's book. So that's our starting point. Now, we've all probably come across the Schwarzschild metric at some point in the past, almost certainly if you've done a general relativity course. So it is certainly the case that the Schwarzschild metric represents the most elementary form of black hole space-time. But So I could go through a derivation of the Schwarzschild metric based on things that you know, but I think it's actually a little bit more illuminating to show you something else on the way. So I'm going to discuss what is usually called Birkhoff's theorem in connection with the Schwarzschild metric. So one usually thinks of the Schwarzschild metric as being describing the gravitational field outside a spherically symmetric body. So So what you'd usually do is you would just simply say, well, I construct a metric which sort of exemplifies the idea of spherical symmetry. So it means that I can construct surfaces of constant time and constant r, a radial variable, telling you how far you are away from the center. Such things would have a metric of a two-sphere. So if I try to construct the metric, I start off with saying, well, at constant r, this radial variable, you would have the metric of a unit two-sphere. So the fact that the thing is spherically symmetric and has some kind of radial variable, r, really more or less encompasses this. I've chosen here r such that the surface area of spheres of constant r is 4 pi r squared. So that's the meaning of putting r here as opposed to some function of r. So the fact that there's r here and not some weird function of r is simply a choice of coordinates. Then what else would you expect? Well, you would usually write down minus v dt squared plus some other function dr squared. And of course, what you usually see is that you think that v and w are functions of r. That's fine, but nobody told you this was a static space-time. They could be functions of t as well. So this could be r and t, and this could be functions of r and t. So that is the line element that we wish to explore. What I'm going to be interested in is just simply vacuum space-times, at least to start with. So let's start with vacuum space-times. These obey the vacuum Einstein equations, RAB is equal to 0. There is a question.
Is there a reason to automatically exclude the dTdr portion of
I think that if there were a dTdr term, the answer is no, not really. You can put it in and discover that it will go away if you really want it to. I will leave that for you. It will be horribly complicated to do that. So what you do is evaluate the Ricci tensor. So you can, after a long, horrible calculation, which I am not going to do for you, if you want to do this, there are three ways you can do it. You can do it in components. This will be completely and utterly horrible. I don't recommend it. You can do it on a computer, Everybody should do it on a computer at least once in their life to discover that it's easier to do it that way. Or, so you need an algebra handling language, and Mathematica will do just fine if you want to construct this thing using a computer. There are packages that do this, so it's not that hard to discover one. It might be a bit harder to discover a free one. Or you can use differential forms to do it, but I have a suspicion that Dr. Stewart did not do differential forms. Is that right? He didn't. I suspect that Professor Gibbons will do it in his course if you're going to it. Is anybody actually going to it? He says starting. You had in mind some other course. Applications of differential geometry to physics, not some general relativity course. So that would make it easier for you, but still not much fun. So I rather stupidly did it by hand rather than using a computer, and this is what I got. It's interesting to notice that if you attempted to look this up in Hawking and Ellis, you will discover that it's not right there, or at least not in my edition. Prime is going to be d by dr, and when I get to it, dot is going to be d by dt. So double dot, of course, just means second derivative. So that's RTT. R is equal to minus V prime double prime over 2V plus V prime squared over 4V squared plus V prime W prime over 4V W plus W prime over WR plus W double dot over 2V minus V dot W dot over 4V squared minus W dot squared over 4VW. I should perhaps reassure you at this point, I don't expect anybody to remember these formulae. R theta theta is 1 minus 1 over W plus R W prime over 2W squared, that's a plus, minus RV prime over 2VW. R phi phi is equal to R theta theta sine squared theta. And RTR is equal to W dot over WR, and all other components vanish automatically. So those are the components of the Ricci tensor. So we need to put all of these equal to 0. So the first stop is RTR. That says that W dot is equal to 0. That means W is only a function of R. So the first thing to discover, of course, is that time dependence cancels out of here. The next thing to do is to stare at these two equations here and notice that they are very similar. This term is rather like this one is rather like this one, but has the opposite sign. This one is rather like this one, and the only real difference is that somewhere there's a W here as opposed to a V here. So if you think about it, you'll discover that if you take the combination W over V of RTT plus RRR, well, that's got to be 0 by the Einstein equations, but this amounts to just V prime over V plus W prime over W is equal to 0. So that tells me that log of VW is some arbitrary function of t. But we already know that that W is independent of t, so that tells you that V is some arbitrary function of t and R. Let's see. So that tells me that V must be of the form, since this is independent of t, must be of the form, let's write it this way. So that tells me that, which way round do I want to do it? V is going to be G of t over W. So we want to use that in here. If you substitute this expression into this form of the line element, you will end up with the following expression. If I can get it off. The line element looks like ds squared is equal to minus some function of t dt squared over w, which is only a function of r, plus w of r dr squared, plus r squared into d theta squared plus sine squared theta d phi squared. Now what you can do is you can simplify this term. Remember that in general relativity you always have the opportunity to do coordinate transformations if you want, to make life easy for yourself. Here is a prime example of doing that. So, here we have some function of t times dt squared. The easiest thing to do is just to redefine the time variable. So I'm going to invent a new time coordinate, t tilde, such that d of t tilde squared is equal to g of t dt squared. So as long as nothing pathological happens to g of t, that's perfectly reasonable. So that t tilde is going to be the integral of g of t square rooted dt. So that's just a coordinate transformation. And you will notice now that what happens is that we have turned a fairly arbitrary space-time that depends on two variables. We've discovered that, in fact, it must be independent of time, namely minus dt tilde squared over w of r plus w of r dr squared plus r squared into d theta squared plus sine squared theta d phi squared. So what we have proved is what is usually called Birkhoff's theorem, namely that spherical symmetry implies static. This is the simplest example of what usually go by the name of black hole uniqueness theorems. we will come across, although we won't do it in detail, many more black hole uniqueness theorems. What about the remainder of the Einstein equations? Well, if you plug it in, all that's left is the following thing. The theta-theta equation, which is 1 equals 1 over w minus r w prime over w squared. So that's kind of easy to integrate up. I won't do it explicitly. If you do this, what you'll discover is that w is equal to r divided by some constant plus r. So what you will see for the metric now is ds squared is equal to, well, you have a minus 1 over w here, so this will be minus into 1 plus constant over r dt squared. I guess it should really be t tilde squared, plus dr squared over 1 plus the same constant divided by r, plus r squared into d theta squared plus sine squared theta d phi squared. So that is the Schwarzschild metric, which you must all have seen before. Now we have to ask, what is the physical meaning of this constant? Well, let's think about what we're actually trying to do here. We're thinking about the space-time outside some body where the gravitational field is spherically symmetric. So there is some region here, perhaps the Earth, a star, a galaxy or something, elementary particle, where there is some matter, RAB is not equal to 0. And then outside it, RAB is equal to 0. The radial variable we've been describing basically takes you out in this direction. And you will see that if you go far enough, you'll end up with just dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared and a minus dt squared here, which just gives you Minkowski space. So r goes to infinity is flat. But you know that if you think about taking the limit of general relativity as you get Newtonian gravity, you know that G00 is equal to, now we have to worry a bit about sign conventions. I think it's minus 1 minus 2 phi, where phi is Newtonian gravitational potential. This is as r goes to infinity. It's just within the realms of possibility you think it's minus 1 plus 2 phi. So, you have all seen the weak field limit, I hope. No? Two yeses? Some puzzled. I'm a little worried about that. Maybe we'll have to do something about that. The Newtonian gravitational potential for an isolated object is just, as we've seen before, minus m over the distance from the thing, where m is the mass. or possibly what you might want to call the gravitational mass. Of the object. So to make the Schwarzschild metric agree with Newtonian physics, what you've basically done is to say this constant is equal to minus twice the mass. And then you end up with the metric in the well-known Schwarzschild form, as first written down by Schwarzschild in 1916, curiously before general relativity was published, in this form. d theta squared plus sine squared theta d phi squared is such a combination, such a common combination of stuff that I will call it d omega 2 squared. D omega 2 squared is the line element on a unit 2 sphere. It's possible that I will at some point use a generalization of that, d omega n squared, the line element on a unit n sphere. I will try very hard not to write below here. I obviously have not quite succeeded yet, but as far as I can tell, that is the boundary of where you can see if you're at the back. The boards in this room are a little bit tricky. So that is the Schwarzschild metric. So there are various things that need to be said about this. The first is that, of course, we derived this metric on the assumption that it obeyed the vacuum Einstein equations. And if you stare at the metric, there doesn't really seem to be anything terribly wrong with it anywhere except two basic places. Well, it obeys RAB equals 0, except everywhere, except possibly well, the only place that it could go wrong is where metric coefficients or the inverse of metric coefficients aren't differentiable, because when you compute the Ricci tensor, you know what you have to do. You compute the Christoffel symbols. That involves taking derivatives of the metric and looking at the inverse metric. Then when you compute the Ricci tensor, you have to look at derivatives of the Christoffel symbols and products of Christoffel symbols. So if anything goes to 0 or diverges in the metric, you are potentially in trouble. So if you look at the metric coefficients, you are in trouble at r equals 0 because this goes to 0. This is singular, and that is singular. So there is difficulty at r equals 0. There is also difficulty when r is equal to 2m, if it's ever equal to 2m. So at those places, there is a difficulty with knowing or being absolutely certain that nothing or something has gone wrong. So you need to investigate very carefully what happens at those two places where these things give you difficulty in order to understand whether saying that the metric, the space-time metric, makes sense as a solution of the vacuum Einstein equations everywhere. So what I propose to move on to is to look precisely at that issue. So Obviously, if you start at r equals infinity and move inwards, you will discover that the first place you come to, provided m is positive, I'm going to assume that m is positive for the moment. You reach r equals 2m, and there the metric is singular. The real question is whether or not that singularity is a physical singularity or not. There is a possibility that it's just simply a coordinate singularity. These kinds of problems are, of course, not unique to the Schwarzschild metric. They hold for, that you have to do the same thing for almost any metric that you discover. The way to tell whether or not something is a coordinate singularity, for sure, is to invent coordinates which are not singular. I'm sure that Dr. Stewart spent a certain amount of time discussing questions about coordinate patches, charts, and atlases, even if he didn't call it that. So the idea is very simple. If it's just a coordinate singularity, you should be able to invent a new coordinate system in which the singularity just simply goes away. The trouble is that there's no deductive way of doing that, which is a little unfortunate. There is something you can do, but this again is a little iffy because it's not guaranteed to produce an answer. So you might say that if something bad had gone wrong with space-time, you might notice that I'm already using rather loose words to describe this. You would expect something unphysical to happen. Now, the only way in which you can discover unphysical things happening would be if scalar quantities diverge or blow up or do something awful. That's because only scalar quantities are independent of the coordinate system in which you calculate them. So what you can do is to calculate a few scalar quantities and see whether they do anything bad. Now, what kind of thing can you calculate? Well, we're dealing with a vacuum solution of the Einstein equations, so the Ricci tensor is equal to 0. All you've got to do to play with is the curvature tensor and derivatives and the metric. Well, the metric is, of course, a tensor. The only scalar that you can find out of the metric and nothing else is basically the dimension. That's not going to do you any good. So GAB, well, that's probably 4, and you'll be happy with that. Scalar quantities built out of one power of the curvature. Well, there's only one. That's the Ricci scalar. It's 0, except possibly where things aren't differentiable. We could leave a question mark there, but you can see that that's fraught with problems. In fact, that already illustrates what's wrong with this approach. Nevertheless, it's a good one. So your next stop would be to say, how about things quadratic in the Riemann tensor? Well, there's one obvious scalar which is not 0, and that's the square of the Riemann tensor. And if you worked out what this was, you would discover it was equal to 48m squared over r to the 6th. So you would be very tempted to say that means that at r equals 2m, this scalar does not blow up. So that seems to indicate that you're all right at r equals 2m. Equally, it seems to indicate that at r equals 0, something terrible happens. I'm not going to tell you what terrible thing happens yet. I can describe what happens mathematically, but I cannot describe what happens physically. So, it looks, based on this, that it's sensible to try and get rid of the coordinate singularity at r equals 2m. So we will go ahead and do that. Now, I reckon that I have 1 minute and 30 seconds left to do that in. I don't think that's possible. So I think we should probably stop there and contemplate how you might do it. I'll do it on Monday, I guess. So, on Monday, we will meet at 10 o'clock, and Professor Green will meet at 11. Well, he won't meet. His class will meet.